Hi, everybody. My name is Mike Zephyr. I'm an associate professor in the Faculty of Business and Economics at the University of Melbourne, and this is the Quantitative Methods Network, or QMNET, here at the University of Melbourne, which is an informal group of researchers across faculties, and at this point across universities, actually, in Australia, who are interested in everything quantitative. And today we've got a great and exciting talk by Keichi Takahashi on accelerating empirical dynamic modeling using high performance computing. And it's kind of a humble title. I think it could be very high performance computing, but so Keichi is an assistant professor in the software design and analysis laboratory at the Nara Institute of Science and Technology in Japan, and received his PhD in computer science at Osaka University in 2019. And in 2018, he was a visiting scholar at the Oak Ridge National Laboratory. Just a very cool place. That must have been incredibly fun. And his research interests include high performance computing and networking. So thank you so much, Keichi, and feel free to take it away.
All right, thanks. Let me share my screen. All right, so thanks for having me. I'm Keiichi Takahashi, and this talk is a follow-up to Gerald's talk, which happened last week, about accelerating empirical dynamic modeling. He mostly focused on the biological or neuroscience part of the project, but this time I will focus on the computational challenges in accelerating EDM. Okay, so the agenda for today is this. So I'll briefly recap what EDM is, and then we'll talk about mpEDM, which is our parallel implementation of EDM that we deployed on a supercomputer. And then we also present KDM, which is a fully GPU offloaded EDM implementation. So mpEDM was a hybrid, CPU and GPU hybrid, but KDM is fully GPU offloaded. All right, so I think most of you were attending Gerald's talk last week, but just want to briefly recap what EDM is. All right, so EDM is a nonparametric method for modeling nonlinear time series data. And the way it works, it is EDM reconstructs the underlying manifold from time series data. And then it uses the reconstructed manifold to do various tasks, like short-term prediction or quantifying the nonlinearity of the time series data. Using CCM, you can identify and quantify the causal relationship between time series data. In this talk, I will mostly focus on CCM, convergent cross-mapping. Okay. So the idea behind EDM is called state space reconstruction. And in SSR, you try to reconstruct the underlying manifold of a dynamical system from observations. And there's a mathematical theorem that states, given enough time lags of observational data, you can actually reconstruct the manifold that is a diffeomorphism of the original manifold, the latent or shadow manifold. All right, and this is called Tarkin's theorem. And then EDM is centered around this idea of state space reconstruction. Right, so the most basic algorithm in EDM is called simplex projection, which is used for short-term forecast. So in simplex projection, you first create a time-delayed embedding of a time series. So here, uppercase X is the time series, and then the embedding, the time-delayed embedding is this one here. So here, I'm embedding X into E-dimensional space using its time lags. So tau is the time lag, and then E is the embedding dimension. And then for each point in the state space, you find its k nearest neighbors. So let's say you want to find the k nearest neighbors of xt in the state space. We call the so the time indices of those neighbors are t1, t2, and then t plus 1. Then we compute the weighted average of those neighbors like this, shown here in this equation. This is how short-term forecast works using simplex projection. This works because the local neighborhoods are preserved in this reconstructed manifold. So here I'm showing a point in the state space and its nearest neighbors, right? And then if you move these nearest neighbors some time steps forward, we can expect that the local neighborhoods are still preserved. So this is why this short-term forecasting works. Now, CCM or convergent cross-mapping is basically simplex projection across two time series. So it works very similar to a simplex projection. So you create a time-delayed embedding of two time series, x and y, and then you find the nearest neighbors of x in the state space. And then you use this neighborhood information to predict y. And then if you can predict y using x with high accuracy, then we say y causes x, y CCM causes x. So this is the basic algorithm, the original algorithm of CCM. Now, the reason we wanted to accelerate CCM is explained by Gerald in the last week's talk. But one of the motivating application for accelerating EDM was this project. So we employed CCM to investigate the causal relationship between every neuron in a zebrafish brain. But the larval zebrafish brain has around 100K neurons. So if we are to do pairwise CCM between all those neurons, it's going to be 10 billion combinations. So 10 billion cross mappings need to be calculated. Okay. So to do this, we initially tried Sugihara Lab's ADM implementation. So Sugihara Lab is where the EDM methods are developed, right? So these implementations are official. So we started here. So Sugihara Lab's implementation is based on this C++ library called CPP-EDM, which is implemented in C++, and it's fairly efficient. And then there are these language bindings that call CPP-EDM. So there's a Python binding called PyEDM, and then there's an R binding called REDM. CPP-EDM internally uses the standard library of C++, and then also LAPACK for linear algebra. So we initially implemented the prototype using CPP-EDM, and then we distributed the computation across 510 compute nodes in a supercomputer called ABCI. This initial run took around 8.5 hours to analyze 53K time series, each having 1.5K time steps. Right, but so this worked. But remember, our goal is to analyze 100K time series, each having 10K time steps. So if we assume ideal scaling, the target time series that we want to analyze will take 60 days to analyze on 510 compute nodes on ABCI, which is infeasible. I mean, you could probably do it using techniques like checkpointing or restarting, but that's going to burn so much node hours, and it's going to be very, very expensive. So we needed to make mpEDM faster. All right. So to make things faster, you basically need to measure what the bottlenecks are, and this is called profiling. So we profiled mpEDM using a profile called Intel VTune, and here's what we found out. So first of all, this graph here is showing the breakdown of runtime when running CCM on the zebrafish brain dataset. So over 50% of the runtime is spent in k-nearest neighbor search, right? So we know that we need to focus our optimization efforts in making k-nearest neighbor search faster. Then we also found out that memory allocation is consuming much runtime, so or more runtime than we expected. About 30% of the runtime is spent in memory allocation, which is unusual for HPC applications. We found out this is because during computation, mpEDM dynamically allocates and reallocates a lot of buffers. And lastly, we found out that there's a large load imbalance between compute nodes. So this figure here is showing the distribution of runtime for each compute node. And you can see that the fastest compute node finishes the computation in 5.5 hours, but the slowest one takes 8.5 hours. So there's a very large load imbalance among compute nodes. And this is because the work was statically decomposed in the prototype application. So we need to do some kind of dynamic load balancing between compute nodes. Okay, so to summarize, we have to make k-nearest neighbor search faster to accelerate EDM computation. And then we need to reduce the number of memory allocations. And then we also need to reduce the load imbalance between compute nodes. All right, so based on these observations, we implemented mpEDM, which stands for massively parallel EDM. Okay, now the key idea behind mpEDM is Gerald's insight that we can reuse the pre-computed k-nearest neighbors to accelerate k-nearest neighbor search. So say you have one time series here, and then you want to do CCM to a number of other time series like this. Here you have like 3 time series. And if we go back to the definition of the CCM algorithm, the prediction for each time point in the time series is computed like this. So for time series 1, so for Y1, the prediction is computed like this. And then for Y2, it's computed like this, Y3, like this. And then if you look at the equation here, you'll notice that the weights for the weighted average are all the same across all time series. And then also the indices, the time indices of the nearest neighbors are also all the same across all time series. So Gerald's idea is that when computing one-to-all CCM, we can use the distances and indices of the k-nearest neighbors. We only need to compute the distances and indices of the KNN search only once. And then we can reuse the results for all time series. So this is the key idea behind improving KNN. Now the pairwise CCM algorithm incorporating this optimization looks like this. So for every time series, we embed the time series into, we first embed the time series into state space using time lags, as I explained earlier. And then we do an all KNN search in this state space. And all KNN search means we compute the KNN search for every point in the data. And then we get this list of nearest neighbors and its distances. We call this lookup tables. And then we use these pre-computed list of neighbors to predict every other time series in bulk. All right, so this reduces the number of KNN searches required significantly, right? But we also wanted to improve the k-nearest neighbor search itself. So we looked into algorithms for doing k-nearest neighbor search in literature. So this is the summary. So roughly there are exact methods for computing KNN, and then there are approximate methods, right? The exact methods is pretty much doing brute force search, the full search of the entire data. And then approximate methods, these methods do not return, they're not guaranteed to return the exact k-nearest neighbors, but they are much faster than exact methods. The approximate methods are further classified into these four methods: proximity graphs, spatial partition or spatial indices, product quantization, and locality sensitive hashing. So these were the methods that we considered. I won't go into the detail of each method, but if you're interested, I will recommend this tutorial at CVPR by Yusuke Matsui, which covers these classes of algorithms pretty well. Okay, so we ended up picking the brute force approach, and here's the reason. So first of all, the data dimension in our use case is relatively low. In EDM, it's usually below 20. So the cost of computing the distances is not that high. And then the number of points, or which is equal to the length of the time series, is below 10,000 in our use case. This is simply because the available data to us is below this number. So this number of points is considered small in KNN search. And we found out that cost of constructing index structures like spatial partitioning trees or k-nearest neighbor graphs, it doesn't pay off if the number of points is this small. And then if the number of points is in this order, we can fit the entire distance matrix on CPU or GPU memory, because it will only take 400 megabytes to store using single precision floating point numbers. Lastly, we needed exact solutions because at that point we didn't know how approximate solutions would affect the result or quality of CCM. So we ended up taking the brute force search approach. Okay, now the next step was to design and implement the KNN search for GPUs. Because we were using a GPU-based supercomputer, we obviously wanted to take advantage of GPUs. Right, so here in this slide, I'm showing the CUDA ecosystem, so NVIDIA's GPU programming ecosystem. On the lowest level, you have CUDA C or C++. And then on top of that, you have programming models like OpenMP, OpenACC, etc. And then on top of that, you have different math libraries and parallel primitives. One of the most famous ones is called cuBLAS, which is a GPU accelerated implementation of BLAS. BLAS is the standard library for doing linear algebra. And then on top of that, you have these different high-level libraries. So for example, the one we used is called rfir, and it has a similar interface to NumPy. There's also CuPy, which is also similar to NumPy, but it's accelerated using GPUs. Then you have libraries like TensorFlow or PyTorch. TensorFlow or PyTorch are usually branded as libraries for doing deep learning only, but in reality, they're actually pretty general purpose. So I have seen people implementing solvers for partial differential equations using TensorFlow. So these are general libraries. All right. In our use case, we choose to use rfir because if you can implement your computation using these high-level libraries, you almost always want to do that. Because as you go deeper in this hierarchy of software, it gets difficult to write your software, and it also gets difficult to optimize it. So if you can implement your computation using higher level libraries, I would certainly recommend to do so. All right, so so far we have the algorithm for doing CCM. We decided to use brute force search for calculating the k-nearest neighbors, and then we also decided to use rfir to do the brute force search. Okay, so lastly, it's about implementing this algorithm in software targeting supercomputers. So to implement software for supercomputers, you need to understand the architecture, the hardware architecture of the supercomputer, and you need to exploit the parallelism in your algorithm to exploit this hierarchical parallel architecture of supercomputers. So here I'm showing an example of a supercomputer, which is Fugaku, our country's fastest supercomputer at this point. Fugaku as a whole system has a computing power of 537 petaflops. And then this cluster is composed of 432 racks of compute nodes. Each rack can compute 1.3 petaflops. And then each rack has 384 nodes, which is essentially equal to a server. And a node can compute 3.38 teraflops. And then each node has 48 ARM cores, each of which can compute 70 gigaflops. So when you want to implement software for supercomputers, you need to design your algorithm that that matches this hierarchy. Okay. In our project, we didn't use Fugaku because it wasn't available at that time, but we used a supercomputer called AI Bridging Cloud Infrastructure, or ABCI, run by the AIST Institute in Japan. So here I'm showing the overview of ABCI. This picture here is showing the data center that we were talking about earlier. And then this picture here is a logical view of ABCI. So ABCI right now has 1088 compute nodes, 1088 NVIDIA Volta compute nodes, and then 120 Ampere compute nodes. These nodes weren't available when we were doing this project. And then these compute nodes are connected using a high-speed network called InfiniBand. And there's also a parallel file system, which are shown here. It's a mixture of Lustre and GPFS. Okay, now if you look at the individual compute nodes, it looks like this. So each compute node has two Intel Xeon Gold Skylake CPUs. And it also has four NVIDIA V100 GPUs. And those components are connected like this using PCIe. Okay, so this is the internode design of PEDM, how work is distributed across multiple compute nodes. So it's a fairly basic master worker architecture. So there is one master that assigns or dispatches work to workers. And then each worker asynchronously fetches work from the master and then executes the work. Each work is basically a one-to-all cross-mapping between time series. Okay, and then the workers asynchronously write the results to disk. We also use a burst buffer, which is like an SSD cache on ABCI to accelerate the small I/O, because parallel file systems like Lustre or GPFS are not good at handling small I/O. So we first write to a burst buffer, and then at the end of the run, we write the results to the parallel file system at once. Okay, now here I'm showing the intranode design of MPEM. It's a hybrid design, as I mentioned, a CPU-GPU hybrid design. So in the first phase, we do the time-delayed embedding on the CPU side. And then we copy the embedded time series to the multiple GPUs that are available on a compute node. And then on each GPU, we do an OKNN search using rfir and compute the distances and indices of the nearest neighbors. Those results are then copied back to the CPU. And then on the CPU, we do a batch prediction of all time series using the algorithm that I explained earlier. All right. So let me explain a bit about rfir. So rfir is a general purpose library for GPU computing. And it's roughly kind of compliant with NumPy. But internally, unlike NumPy, rfir invokes different vendor-optimized libraries. So on NVIDIA GPUs, rfir invokes cuBLAS for linear algebra, cuSparse for sparse linear algebra, cuSolver for solving linear systems, QDNN for doing neural network calculations, etc. All right, so the code using rfir kind of looks like this. I'm showing a snippet here. All right. So using rfir and some other libraries, we implemented mpEDM, a massively power EDM designed for GPU supercomputers like ABCI. So far, mpEDM supports simplex projection and CCM and pairwise ECM, as I explained. Okay, the code is available here, And the paper was published at this conference called ICPA ES. All right, so here's the evaluation results. We're running CCM. So we tried 3 large data sets that haven't been analyzed before using EDM. The first one is it's called Fish1 Normal, which is basically the recordings of a neural activity of a zebrafish. This data set has 4,150 time series. This is actually flipped. So the data set has 53,000 time series, and each time series has 4,150 time series. Time steps, sorry. Okay, now this data set took 8.5 hours to analyze using CPPEDM, the official EDM library, using 512 compute nodes. But using mpEDM, using just one node, it took about 2,000 seconds to analyze. This is around half an hour. And if we scale up to 512 nodes, it only takes 20 seconds to analyze the entire data set. So if you compare 8.5 hours and 20 seconds, it's actually 1,530 times faster. Then not only is it faster, but it's also cheaper. So if you can wait half an hour using one compute node, which I think is reasonable, the required node hours is 8,000 times less. So a node hour on ABCI costs around 220 Japanese yen, which is $2 US. So to do a full run using CPPEDM, you need 8,700 US. We didn't actually pay this money because we have an agreement with the institute that runs ABCI. But using mpEDM, you only need one node and half an hour. So you only need to pay $1 US. So this is this much cheaper. Okay. Now we also analyzed 2 other data sets called subjects 6 and 11, which both have around 100K time series and 4,000 time steps, 8,500 time steps each. We couldn't run this using CPPEDM because it would take too much time. But with mpEDM, we were able to analyze. Subject 6 took only 100 seconds, and then subject 11 took 200 seconds. So this is a lot of speed up, obviously. Okay, we also evaluated the internal scalability. Here we are scaling the number of compute nodes to use in the computation. As you can see, the runtime is scaling and is reducing pretty well. Here I'm showing the relative speed up. So until 64 compute nodes is scaling linearly. But then there's a bit of slowdown, which happens around here, which we found out it's caused by the initialization time of the GPUs. So since the computation takes only 20 seconds to run in this case, the time required to initialize the GPU becomes a significant overhead in this case. But it's scaling pretty well. Okay, and here we measure the intranode scalability. So if we increase the number of time series or number of time steps, the runtime increases like this, which is quadratic. And then we also measured the breakdown of runtime. on the left-hand side, here we are fixing the number of time steps to 10K, I think, and then varying the number of time series. And we can see that the time for lookups or the batch prediction becomes dominant as you increase the number of time series. On the other hand, if you increase the number of time steps, the time for the KNN computation becomes dominant. All right. So these are the performance evaluations of mpEDM. So using mpEDM, we were able to achieve the goal of analyzing this whole brain neural activity data set. And mpEDM was significantly faster than CPPEDM, but several challenges remained. One of which is rfir's KNN search works, and it's reasonably fast, but it's not optimized for the type of KNN search required in EDM. So, for example, in EDM, as I explained, you first need to embed the time series into state space, and then you do a KNN search in the state space. But we can further make this computation more efficient by fusing those two. So you could embed the time series into state space while doing the KNN search. This makes the computation much more efficient because it will reduce the memory accesses required. Okay, and then also the number of neighbors that we want to compute is usually small in EDM, usually less than 20, but rfir's KNN is tuned for a larger K. So if we could modify the algorithm to target smaller K, we could make it even faster. Then another big challenge is the predictions. The batch prediction phase was executed on the CPU in mpEDM. We actually tried to implement the lookups on GPU using rfir, using these features in rfir, but the performance wasn't great. It worked, but the performance was poor. So we needed another approach for implementing lookups on the GPU. And then lastly, there is the problem about performance portability. So we were mainly targeting ABCI, but obviously we also want to run on other compute nodes, compute servers and laptops that don't have NVIDIA GPUs. So we had a separate CPU-based backend, which has a completely different code base. So we had to maintain the GPU backend and CPU backend, which implement the same algorithm, but two different code bases. So we wanted to merge those CPU version and GPU version into one. Okay. Which brought us to implement the KDM, the successor of mpEDM. All right, so before explaining the details of KDM, I first need to explain the high-level architecture of NVIDIA GPUs. So here I'm showing a picture of the internals of an NVIDIA GPU. So an NVIDIA GPU is composed of multiple processors called streaming multiprocessor, or SM. And then each SM has its own L1 cache registers and a thread scheduler. And then each SM has many CUDA cores, which does the actual floating point number calculations. And then there's also a shared L2 cache, which is shared across all the SMs, and then a global memory. All right, so what oh, and the memory bandwidth also matters. So a GPU is fast in computation, but the memory bandwidth is actually not fast enough. So if I remember correctly, NVIDIA V100 can do 10 teraflops of single precision floating point calculation. But if you look at the memory bandwidth, it can only provide 800 gigabytes per second. So it's actually not fast enough to keep up with the computation. L1 cache and L2 cache have higher bandwidth. L1 can do 14 terabytes per second, and L2 can do 3 terabytes per second, which is much higher than the memory bandwidth. But this is still not enough to keep up with the computation. So it's very important that you try to maximize memory reuse to minimize the memory accesses to get viable performance on a GPU. Yeah, okay, so this is the basic hardware architecture. And then I also need to explain the software programming modeling in CUDA. So a software in CUDA is composed of grids of blocks of threads. I'm going to explain what that means. So a CUDA program is composed of the CPU code and the GPU code called kernel. And then the CPU code launches the GPU code like this. And then here I'm showing a GPU code for doing vector scaling and addition. And this GPU code here will be scheduled on the GPU. The program model here it looks like this. So there are multiple threads organized into blocks. So a block can have around 200 or well, up to 1,000 threads. Then those blocks are organized into grids. So you have to make sure that your computation also has this kind of hierarchical parallelism, right? And then these threads and then the thread blocks are scheduled to hardware like this. So a GPU can execute multiple grids, right? And then each streaming multiprocessor in the GPU can execute multiple thread blocks. Then each CUDA core in the GPU executes multiple threads in a thread block. So this is how the software and hardware are mapped in CUDA. All right. So to write CUDA software, you need to make sure that you find and map parallelism in your computation. And you also need to do a lot of memory optimizations to make sure that you maximize cache hit rate. Okay, so these are the basic hardware and software architecture of CUDA. All right. So given this programming model and hardware design, we implemented the ABCI algorithm from ground up. All right, so for k-nearest neighbor search, the implementation looks like this. So it's still a brute force approach. So we first do an all-to-all distance calculation. But the distance calculation has a lot of parallelism. So each element in the distance matrix can be computed independently, right? So what we do is we make each thread block calculate one row in the distance matrix. And then each thread in a thread block calculates one element in a row. Okay, this is the basic mapping of parallelism. And then we also do memory optimizations. One of which is to cache the time series into shared memory. That's the L1 cache in each streaming multiprocessor. We do this because if we cache a portion of the time series, these elements of the time series get accessed many times, so we can significantly increase the cache hit rate. Then another optimization that we did is to do the time delayed embedding on the fly, so while doing the distance calculation. This is also very good for the performance, because if you, for example, do the time delayed embedding before the distance calculation, if you write those coordinates in the state space into a large matrix before the distance calculation, this embedded coordinates get actually very large, and reading those coordinates, those embedded coordinates, will take much time and become the bottleneck in the distance calculation. So we do the time delayed embedding on the fly while doing the distance calculation to minimize memory traffic. Okay, and then we do a top case search. The top case search is implemented like this. So just like in the distance calculation, we map each thread block to rows in the distance matrix. And then each thread in the same thread block will hold a local priority queue that maintain the top k elements each thread has seen. All right, so here I'm showing those local priority queues. Each queue is maintained by different threads. And then each thread scans a segment in the distance matrix and updates this local priority queue. Then after all elements are scanned in a single row, a leader thread merges those local priority queues into one into a final priority queue and writes to memory. So this design is not novel, but we took it from several other works, several other prior works. All right, so this is how k-nearest neighbor search is implemented in KDM. Lastly, I'm going to talk about the batch prediction phase. So given the k-nearest neighbors that are computed, that are pre-computed, and all the time series, we want to predict all time series at the same time in parallel. So here we map each thread block to each time series. And then each thread in the thread block will predict one time point in the time series. All right. We also do a memory optimization here. So we cache the target time series in shared memory because this will minimize the memory accesses, the global memory accesses. And also, since the time series is randomly accessed, caching the target time series in shared memory will make it faster because the global memory cannot handle random access very well. All right, so I talked about the KNN search and then the batch prediction or lookup. Lastly, I want to talk about the library that we use to implement this. So we used a library called Kokkos, a performance portability framework. And what this library allows you to do is it allows you to write your program only once, and then it will run on many different architecture with decent efficiency. There are other libraries that allows you to do portable programming across CPUs and GPUs, but those libraries are not necessarily performance portable. So meaning your code will run on CPUs and GPUs, but may be very slow. But Kokkos makes sure that your code runs with decent efficiency. Right. We also picked Kokkos because it has lots of different tools to debug and optimize your code, and also there are several libraries based on Kokkos, like the Kokkos kernels. It implements dense and sparse linear algebra. All right, so I'm gonna skip this because it's probably too detailed. All right, so the resulting implementation is called KDM because it's EDM based on Kokkos, and KDM supports simplex projection, CCM, and ESMA at this point. The CPU version of KDM can be installed from PyPy using pip like this. You can try it out today, but the GPU version currently needs to be installed from source because of a limitation in Kokkos. Kokkos right now doesn't support building GPU binaries targeting multiple architectures, multiple GPU architectures. So you need to compile it to target your GPU. So lastly, I'm going to talk about the evaluation we did for KDM. We used two servers at the Salk Institute. One is called ICA, which has two Intel Xeon Gold CPUs, one NVIDIA V100 card, and then another server called Aori, which has two AMD EPYC CPUs and 1 terabyte of RAM. So these are the results when analyzing real-world data sets. So the rows are different data sets. And here I'm showing the results measured on ICA, which has a V100 card and the CPU. And here I'm showing the results measured on Aori, which has only EPYC CPUs. As you can see, KDM is faster than mpEDM in most cases. So, for example, with this large data set, which has 100K time series and 4,000 time steps, we achieve 5.5 times speed up over mpEDM. This speed up mainly comes from the fact that we ported the batch prediction to GPU, whereas on mpEDM, the lookups were only executed on the CPU. We also get 4.4 times speed up with this subject 11 data set, which is even larger. For some data sets, KDM is slightly slower. Like here, with this gene expression data set, you get a bit of a slowdown compared to mpEDM. But overall, KDM is much faster than mpEDM. And even on the CPU, it's faster than mpEDM. All right. Here, I'm showing the micro benchmarks for KNN search. So here we took an artificial data set that has 10K time steps and measured the time required for doing the k-nearest neighbor search phase. As you can see on EPYC, KDM is slightly faster than mpEDM. On the V100 card, And KDM is 6.4 times faster than mpEDM when equals 1. But as you can see, the top K search, or the partial sort, rapidly gets slower when you increase the number of embedding dimensions. This is because since each thread on the GPU maintains a local priority queue, since the top K elements need to be stored on shared memory, if you increase the number of K, you need more shared memory to store the top K elements, which in turn means you can schedule less threads on each SM. So that's why we get this slowdown. But up to the 20 KDM is always faster than mpEDM. So for the target K, KDM is always faster, so that's okay. We also did a similar evaluation using for lookups, using this kind of artificial data set. And we can see on the EPIC again, KDM is slightly faster than mpEDM. And on the V100 card, KDM outperforms EPIC roughly 3 times to 4 times. Note that we don't have the results using mpEDM on V100 because of the limitations I mentioned. All right. We also did a roofline analysis, which is a method to assess the efficiency of computational kernels. So these roofline plots indicate how much of the theoretical performance the application is achieving. So on the horizontal axis, we are plotting the arithmetic intensity, which is how many floating point number operations we did per byte read from memory. And then the vertical axis is performance measured in gigaflops. Right. And then these roofs indicate the theoretical peak that is achievable for a given arithmetic intensity. All right, so on EPIC, for example, if we look at this pairwise distance kernel, you can see that it's bounded by the L3 cache bandwidth. And we are pretty close to the roof. So we are close to optimal performance. On the V100, initially, we are hitting the 8 PM bandwidth. So that's good. But if we increase the number of embedding dimension, we're far from the theoretical performance. This is because if we increase the E, we found out that the kernel is saturating the load store units in the streaming multiprocessors. So even though we are not fully utilizing the memory bandwidth, we are saturating the load store units. So this is also pretty much what we can get on V100. Right, so a similar analysis was done for the lookup kernel. Here we are also getting pretty much the optimal performance on both platforms. All right, so in conclusion, using KDM, we achieved pretty much the optimal performance on both AMD EPIC and NVIDIA V100. All right, so that was the last slide, my talk. So I just want to acknowledge those people, my collaborators, and here are the list of software that I talked about. And then those 3 papers there are several other papers, but those are the main papers published about the computational aspects of this project. All right, thanks for listening.
Thank you so much, Keichi. That was really engaging. Does anybody have any questions? I'm happy to kick it off here with, so initially you mentioned that I think it was in the first 10 or 15 minutes, that the 400 megabyte value was storage based on single precision.
Yeah.
So I was wondering if you were using FP32 or 64, or just what the level of precision was, and then if you'd done any tests looking for the effects of reductions in precision on CCM or EDM results.
So the entire computation was done in FP32. So
right.
We didn't use double precision. That's mainly because the data sets we use has a limited dynamic range. So there's no need for using FP64 in our use case. We haven't tried FP16, which we probably want to, but yeah, as you said, we haven't looked into the performance and accuracy trade-off, not yet. So,
right. Yeah, I think most of the real data sets are, I mean, they don't benefit from FP64 because none of the measurements reach that precision.
Right. Yeah, I mean, there's so much work being done also, obviously, on kind of lower levels of precision, mixed, new mixed precision types. It just seems like that could be an interesting, avenue for additional research on, ways of speeding this up.
Yeah, so the same thing could be said for the approximate nearest neighbors that I talked about.
Right.
So
right.
I'm pretty sure approximate KNN works with ADM, but we haven't evaluated that. Not yet.
Right. Okay, cool.
But I mean, for practical purposes also, I think this is pretty much the data that you can generate. The only thing that we have there is like, I wanted to remark that, for example, that, although almost always the GPU is better, in the case of the gene expression data sets, it was really difficult to get a lot of steps. So the time series are really expensive to make. So if you make a time series of gene expression, it'll easily cost you $30,000 to $50,000 to make one data set. And that data set, you can actually have like basically 100 time points. If you got 100 time points or less, then you're probably better off with KEDM in a CPU, not in a GPU.
Mm.
That's what the data showed there.
Right. Pat, did you have anything you wanted to ask?
Yeah, I had a couple of basic questions. One was like, for the different GPUs, does it matter, like what should you be looking at for getting like the most performance? Like if you kept the number of CUDA cores the same, like moving from Ampere to Pascal to Volta, like do you know, is there any big jump there? Or I think something like the newer ones have more freedom in the independent thread execution or something along those lines. Yeah, just wondering if you had any thoughts on that.
Yeah, so if you programmed on a GPU later than Kepler, if I remember correctly, the fundamental architecture didn't change since Kepler. So if your code runs on, GPUs later than Kepler, then it will run on Volta, Ampere, and possibly eGPUs in the future. Then about, you mentioned about independent thread scheduling, right, in Volta. Yeah, so in our case, I remember the top key search phase requires, it actually benefits from independent scheduling because different threads are looking at different data. So when updating the priority queues, different threads are actually executing different branches. So in our use case, independent thread scheduling, since Volta helped the performance. Yeah.
Okay.
Oh, and another thing is, since Volta you have tensor cores, right? So tensor cores are basically matrix multiplication engines on a GPU. So if you have a lot of matrix multiplications, you want to make sure that you use tensor cores.
I thought afterwards you compare with Ampere also, right?
Yeah, yeah. Oh, sorry.
Yeah, I ran on Ampere. Actually, I ran on RTX 3090, which is an Ampere generation GPU, and on A100, which is a HPC Ampere GPU. But I don't remember. But it wasn't, I think the improvement since Volta was less than 50%. That's what I remember.
Can I just ask, are you planning on releasing any kind of Python bindings for the mpEDM, or do you just recommend to use the KEDM now?
Yeah, I recommend using KDM. And KDM has Python bindings.
Yeah, that's what I thought so. Can I just ask a really general question? You talk about the time series, the number of time points in your time series, but what's the bandwidth of the signal you're actually interested in relative to that? I mean, sample rate, essentially. What are we talking about?
Okay, so I'm going to forward that question to Gerald because he provided the data.
Can you say that again?
Well, I'm interested in essentially talking about the computation costs for the number of time points. So I'm interested in what's the bandwidth of the signal that you're sampling? So what's the sample rate that's important? I mean, are you talking about Nyquist sampling or what?
Well, I mean, yeah, we generally go around Nyquist, try to go Nyquist sampling, but most of the time that's that depends on the nature of the experimental system, that it's possible or not possible. So that, I mean, depends on, like, for example, in the imaging stuff for the brain is like microscopy, but the sensors themselves are kind of slow compared to the real dynamics of the thing. So it integrates over time. So then there's like the time scale that which we go here is like, 2 to 4 hertz. That's sufficient for what we're looking at. But for example, the underlying dynamics that are underneath it are actually much faster than their range of 50 milliseconds.
Okay.
So, but that's not accessible because the sensor for that doesn't exist or doesn't exist at scale. So for example, yeah, if you put individual electrodes, you can sample much faster than that, but like upwards of like 1,000 hertz, but you can only do a handful of them.
Right. Yeah, I'm just coming at it from a sort of a different perspective where we can sample much faster than the underlying signal. And so I'm talking about MEG neuroimaging here. So
yeah, so for the calculation is like if you sample faster, you have this expenditure in computation that doesn't give you anything. So you downsample. I have things, for example, for respiration, where we sample at very high rates, that I had to downsample because I think that had like a 10 kilohertz or something like that, and then I just downsample it to about 1,000 volt, and it was just fine.
okay.
Actually, it was actually better.
Right.
Yeah.
Okay. Thank you.
Yeah.
Very
And that's one thing that's one thing that I get asked sometimes too. If I'm talking about this, people say, well, what kinds of data requirements are there for this? How frequently do I need to sample a given system? And the response seems to be, Gerald, like you're saying, it depends on the nature of the system. So kind of the intrinsic frequencies at which it changes or the rate of change, et cetera. But then also, we have so many different constraints in different fields on the frequency of measurements that we can take and the quality of the data that we get from those, that I think one thing that needs to be emphasized is that you have to limit your generalizations about a system to the nature of the sampling. So, there's no free lunch. I mean, it's not like you don't, because you're using this new nonparametric method, you get out some of the problems associated with generalization that derive from a research design. So we're always limited. We're always stuck with those. And so just saying, okay, well, I can make generalizations at a given frequency, based on a given frequency of measurement.
Depends also on how many complex behaviors you're observing in that system. So for example, typically I would want to have, when people ask me this, I would actually see at least 4 events of the same thing, of them as many types of events you have in there. So it's like if you actually have let's say large swings and small swings, or swings by a different component, basically, you want to see at least 4 of each in order to get, and then you have sample at a rate that you can actually observe those events.
Right. You want to see it change within the space.
Yeah, exactly.
You want it to travel common paths.
Basically, you want to have you want to have at least a few passes of the same trajectory, so you have a sense of whether, if you were to able to calculate local Lyapunov exponent, you could.
Right.
Yeah.
Right. You need enough information from neighbors to make it work, essentially. Right.
Yeah. But if you only have, let's say 4 passes, then your dimensionality gets reduced probably around 3, because you need, to make a simplex, you need the 3n plus 1 for your embedding dimension. So basically the number of passes that you actually have in that local neighborhood will require the number of neighbors that you could actually get in theory from the passes that you actually have there.
Right. Which is kind of interesting, because usually, Will, it sounds like in your kind of case, people are probably desiring the need to downsample. Like, oh, I got this very high frequency, these very high frequency measurements. But if what that does is shorten the overall duration so that you fail to get enough change along the underlying attractor manifold, then you're going to run into problems.
You want to downsample something that's oversampled, but the actual real time that you sample, you don't want to reduce that.
Yeah,
that's right. Yeah.
You don't want to reduce the number of events.
Yeah.
Right. And you get different dynamics emerging at different time scales. So you also have to be sensitive to that, I think. And so again, I guess, I don't know, Gerald, how do you think about that? I've been up until now kind of thinking about that just in terms of the nature of the generalizations. We're describing a system, how it functions at a given time scale. And so we just have to make generalizations that are consistent with that.
I scan through all time scales.
Right.
So now, especially because we have KEDM, we can actually afford to scan all possible time scales.
Right. Right.
Yeah.
Right.
Different tau values, right?
Yeah, different taus. You could just vary the tau, to your heart's content, or until you don't find anything.
Yeah, I guess you could use some ensemble techniques too to aggregate results. It'd be hard to interpret, but you could do prediction in theory very well at multiple time scales.
Yeah, you can. Actually, we actually do that.
Yeah.
For example, for some of the basically the geophysical data, whereas the process is kind of slow. Like for example, the El Nino ENSO compared to the Pacific Decadal Oscillation that you actually have in sea surface temperature. One is like the 20-year, the other one's the 3 to 4 year, time scale. And then you can actually make a model that where you actually combine both of them into one manifold that has the dynamics of both on top of each other.
Right.
So you can do that, but you just have to increase the dimensionality of it to account for it. But you can actually have the lower dimensional embedding where you only look at ENSO, and you can also have the independently basically another embedding at a different tau where you only capture the Pacific Decadal oscillation. So you can do whatever, but you can actually put both of them together also.
Yeah, of course. Yeah, with a high enough dimensionality, you'll capture
Exactly, just
everything.
increase the dimensionality in order to capture
Yeah.
that.
Right. Right.
Oh.
That's interesting. Well, thank you so much for your time and that excellent presentation. I mean, there's obviously so much work that goes into something like that. You know, the nights and weekends spent testing and optimizing and everything else. So it's really exciting to see the results pay off so fantastically.
Yeah, to produce a tool that other people can use saves us trying to do optimization. It's fantastic.
Yeah, that's right.
Yeah, I'm super happy with this. It's like, I mean, Keiichi has done like an amazing job, you know, having it to a level that is like, I think it's not just about anybody and everybody can use it as long as you have basically an HPC server.
Yeah, that's right. That's right. I think we're all going to log off and go buy one.
Well, even on a laptop, it's faster than mpEDM.
Right.
Yeah. I mean, mpEDM is already like, it was a significant improvement over the original R and basically R and C++ hybrid code that existed in the original REDM. That's where we started. So you actually look from the very beginning from where we started until now, it's like a 122 million fold speed up.
Right, or 122 million unfolding speed up.
Yeah.
I guess we're talking about the manifold.
Yeah.
Thanks, guys. Thank you so much, Keiichi. I really appreciate your time and this contribution to the scholarly community and your talk today. Thanks so much.
Thanks.